Now let's nerd out even more with the normal curve, since it's anything but normal. So the normal curve is a bell-shaped histogram that many histograms resemble. And I'm gonna really quick just kind of draw what it looks like. And we have seen that a lot of data can be normally distributed. We've also seen that the normal curve just kind of appears a lot when we're doing simulation. So I'm gonna today talk about the standard normal curve. And it's important to make this distinction between just a general normal curve and the standard normal curve. So the standard normal curve is a special kind of normal curve. It looks the same, it's still bell-shaped. The only thing is it is set to have an average of 0 and an SD of 1. So for the standard normal curve, if I was gonna draw it, it's still bell-shaped, but I know for sure that right in the middle at the average and the median, this is gonna be 0. And a lot of times you'll see the standard normal curve drawn going one standard deviation in either direction. So usually we draw up to 3 on either side. So 1, 2, 3, and then -1, -2, and -3. And like I said, so both the average and the median are 0, and the standard deviation is 1 for the standard normal curve. And the x-axis is measured in something called standard units, or I like to call them z-scores. I feel like they're more often called z-scores in statistics. And standard units are basically units with no units. So you can convert any units to standard units, whether it's dollars or inches or anything. And we're gonna look at exactly how to do that. The last thing about the standard normal curve is that the area under it is 100%. So if we think about all of our data that follows the normal curve, that is 100% of it, and then we can look at what percentages are between different z-scores. So like I said, many histograms are close to the normal curve, and the reason that we care about this is because you can actually use the standard normal curve to estimate percentages for the data. And this helps us out a lot. We don't want to be drawing histograms, or even with Python, sometimes it's difficult to actually see those percentages just from a histogram. So we can do this, but first we have to kind of scale the data to the values of the standard normal curve, or convert our data to z-scores. So in other words, we have to change that x-axis to have an average of 0 and an SD of 1. And we can do it by converting to z-scores, or standard units. And standard units have a nice, easy formula. I like to think of it as value minus average divided by standard deviation. So you're taking your value that you're concerned about, seeing how far it is from the average, and then dividing by the standard deviation. So to interpret these z-scores, to think about what they mean in the real world, they tell us how many standard deviations above or below average a value is. So if your z-score was 1, positive 1, that means you're 1 standard deviation above the average. If your z-score is -2, it means you're 2 standard deviations below the average. And like I said, the standard normal curve has this nice table attached to it that we can use to answer questions after we convert to z-scores. And we want to make sure to only use this standard normal curve if the histogram looks like the normal curve. Because essentially what we're doing is we're saying we have a histogram that looks roughly normal. Let's just say it looks something like this. And we're saying we're going to estimate this histogram to be the standard normal curve. If our histogram didn't look normal, like let's just say our histogram had a long right-hand tail, something like this, if we tried to use the normal curve to estimate percentages, we'd be off because it doesn't line up. So let's go ahead and look at the table. But I guess before we do that, I want to think about z-scores in terms of their values. So your z-scores can be positive, your z-scores can be negative, and your z-scores can be exactly equal to 0. So Wade, if you have a positive z-score, what does that mean?
So from my understanding is it's going to be everything that is above the median value.
Yes, exactly. So a lot of times we like to say if your z-score is positive, you are above average, or in this case, above the median, because the average and the median are the same. They're both 0. So you are above average if your z-score is positive. What about if your z-score is negative?
So below average.
Then you're going to be below average. So a lot of times students will ask, can you have a negative z-score? Because we know we can't have a negative standard deviation, but does a negative z-score make sense? And it does. It just means you're below average. And then if your z-score is 0, you are exactly average, which in this case is also the median. So keep that in mind. It's easy to calculate these z-scores, and sometimes it's easy to kind of forget what exactly they mean. So here is our normal table, and this is the table of standard normal percentiles. So in this series, we're going to use a normal table with percentiles, meaning it's going to give us the area to the left of that z-score. So it says the table entry provides the area under a standard normal curve to the left of a z-score value, also known as the percentile. This is also known as the cumulative distribution function, which we're going to dive into a bit more in this series as well. But the standard normal distribution we know has a mean of 0 and an SD of 1. So once you convert your data to z-scores, you can go ahead and use this table. And the way it's read is basically saying if your z-score is 1, let's just say your z-score is 1.0, I'm going to go down to 1.0, and then we just want our decimal points after the 0.0 to be 0. So this means that at 1, at a z-score of 1, there is 84.13% of the normal curve to the left of it. So this will make a lot more sense once we get into an example. But it's important to point out too, there are a bunch of different normal tables that exist in the world. Some give percentiles, some give the area to the right of a z-score. I've seen and used normal tables that give you the area between the positive and negative version of the z-score. So it's important to know that this one gives you the percentile. So before we do an example with data from a context of a problem, let's just look at how to find areas under the standard normal curve to make sure that we're really good with that. So for puzzle 1, it says to find the area between 0 and 1. So we know on the standard normal curve, 0 is always in the middle and the standard deviation is 1. So I always like to go ahead and shade the areas that I want, because I can kind of think, if I know the whole normal curve is 100%, what percent am I shading? And I can make an estimate before I actually find the calculation. So 0 and 1 is the area that I want. And if I think about how to do this, if I look on the table, I can't look up anything that just gives me the value of 0 and 1, right, Wade?
Yeah, we're always going to have all the area to the left, so it's going to include some area we don't want.
Right, it's going to include some area we don't want. So let's look at these two z-scores. If I look up 1, I can figure out what's the area to the left of 1. And we actually just did that on the table. I think that was the example I used, 1.0. The area to the left is 0.8413, or 84.13%. So this area to the left is 0.8413. But that's not my answer, because I need to subtract the area to the left of 0. And I could go ahead and go to my table and say, okay, 0, it looks like the area to the left of 0 is 50%. Or I could say the normal curve is symmetrical. That's a nice property of the normal curve, the standard normal curve. So I could have said, all right, 0 is always going to be the 50th percentile. So this is 0.5. So then to get the area I want, I can just subtract them. So wait, if you can do 0.8413 minus 0.5, that will give me my desired area.
So that's going to be 0.3413.
So 0.3413, and that is about 34%. And if I look at this normal curve, this standard normal curve, it does look like about 34% of it is shaded. Let's keep going. Next, it says to find the area below 1. So I am going to mark 1 and shade everything to the left.
Well, this looks like an even easier problem.
Right, this one seems a lot easier. We already know this, right? We just saw that the normal table tells us exactly that. The area to the left of 1 we saw was 0.8413. And that is my answer. I don't even need to do any math. 0.8413, the normal table tells us exactly the area to the left. So that's really nice. If it asks for a percentile, we just have to look at the normal table. Ooh, this is an interesting one. So the next one says to find the area below -1. So now we're looking at -1. And if I shade that, it looks like a smaller percentage than the area below 1. So Wade, what do you think I can do to find this?
So this is tough because the table only has positive values.
Right, if we look back at our table, I don't see any negative numbers.
But we know the normal curve's symmetric, so we know that everything that's to the left of 1, we know that of -1 is going to be 1 minus everything that's to the left of +1.
Exactly. So Wade is exactly correct. If we think about the normal curve, it's nice and symmetrical. So the area to the left of 1, we know is 0.8413, about 84%. And then the area to the right of 1 is going to be 1 minus that, right? Because the whole normal curve has to be 100. And since it's symmetrical, these two, we kind of call them tails, are always going to be equal. And a lot of times in statistics, you'll see the normal curve divided into a middle area, so the area between the negative and positive z-score, and two tails. And so I know that this tail is going to be 1 minus 0.8413. And because the normal curve is symmetrical, that's going to be the exact answer of the tail that I want. So Wade, what do I get for that?
So that tail is 0.1587.
All right, so that is 0.1587, or about 16%. So it does get a little tricky when we're looking at negative numbers, because you kind of have to think about the curve being symmetrical, think about the percentile that you can get, and then how that relates to what area you want. So very last one, it says to find the area between 1 and 2. And I'm going to go ahead and shade that. I have 1 and 2. And again, if I just look at the normal table, it doesn't give me that exact area, but it does tell me, I do know from all of these problems, the area to the left of 1 is 0.8413. And then I can also look at the area to the left of 2. So if we go back to our normal table, we have 2.0, so 2.00. And it looks like the area to the left of 2 is 0.9772. So this is 0.9772. And if I just go ahead and subtract those, I get the exact area that I want. So I have 0.9772 minus 0.8413.
And that is 0.1359.
0.1359, so just a little smaller than the area we got above. So those are just a few quick examples showing how we can find the area between z-scores, or the area above or below a z-score. And this is going to come into play when we have actual data that we can convert to z-scores and then put this in terms of a context. But the standard normal curve is really nice because it allows us to do this quickly without having to draw the actual histogram.